through. And I'm going to go through them, not exhaustively, but in a way that covers a set of points. And as normal for my comments here, I'm weaving together some perspectives from Eugenia Cheng's book, Superior Volume, Joy of Abstraction, with some of the themes from this book and beyond. And what Eugenia Cheng comments in this area of universal constructions or universal properties, she characterizes it fundamentally as the idea of characterizing something by the role it plays in some, this is content, I think it's actually context, I believe. And looking for sort of extremities and sort of exemplars or the most extremal versions of something in a particular category. And she notes that it's key to the whole idea of category theory. So this notion of universal constructions, whether they be things like terminal objects and initial objects, or be things like products and co-products, or things like pushouts and pullbacks. These are fundamental constructions, and there are some others as well, like with exponential objects that also, play a really big role in category theory. And what we're dealing with here is an incredibly powerful and eye-opening way of identifying objects from networks of relationships. The focus here, and the focus in category theory, is very much on the connections. And we saw, to a degree last time in our discussion of U&A dilemma, still up on the board, that really we are characterizing the content of an object through its connections with other objects. We can completely describe an object within a category, its meaning, as it were, not by focusing somehow on its intrinsic properties, objects are just dots, but how it relates to other objects. And in the U&A dilemma, what we saw is the various types of mappings in from representables to an object. If we consider them, we can completely describe sort of the set of data there associated with that object in the pre-sheet. So category theory puts our attention on the network of relationships and defines these constructions that delineate objects of interest, kind of the best, the essential, the one-stop shop object, the most efficient way of capturing certain information in a category. Richard Southwell, in his great videos on introductions to category theory, talks about universal constructions describing categorical perfection. It's a notion of like the perfect way of capturing information of two pieces of information side by side. That would be the product. Or capturing a choice of either this or that. That would be a co-product. Capturing sort of compatible pairs of objects, for example, that would be a pullback, like shirts and pants of the same color. So these constructions are defined for a particular category based on the network of relationships in that category. And we're going to be talking about two of them to get started, terminal objects and initial objects. And what you'll see is there's this eerie, well, it can be at once eerie, but in once exciting ways in which these ideas generalize things we're very familiar with. These ideas point to things that are at once very familiar, but on the other hand, seem so novel in some ways. And we'll see that like terminal objects and initial objects and products and co-products and pullbacks and pushouts to a lesser degree, these all are familiar notions from SAT, particularly the first four of those. Just like monics and epimorphisms or split epimorphisms are familiar as injective and surjective functions from SAT. So these will be generalizations, and we'll see them in a lot of categories. So the first universal construction is what's called a terminal object. And the terminal object is, again, it's an object in a particular category. We talk about a category having a terminal object. If there's more than one, they're uniquely isomorphic to each other, so we might as well consider it one. But there may be some categories where there are some categories where these don't exist. If it exists, what distinguishes it, whether or not it exists, is if there's an object such that for every object in the category, including itself, there's a unique morphism from it to itself. I'm sorry, from that other object, C, to the terminal object. So for every object in the category, there has to be a unique morphism from that other object to this terminal object. Not more than one, just one. There has to be exactly one. And that includes from it to itself, just one. It turns out this is it's an example of something called the limit, and we'll be talking about limits. So limits are quite important, actually, in the area of sheaves. And they're quite sensible. They'll grow on you, like Munchkin category theory. But this is terminal object. So this would be, if this were a category, we have these objects. And there's some morphisms here drawn. I think this may have been from David Spivak or Brendan Fong. Each of these objects on the right has a unique morphism. It may not be really obvious, but a unique one to this object here. And the fact that every object has a unique morphism to this one, and this one has a unique morphism to itself, marks this in this category as the terminal object. It's kind of the terminus for all these other objects. They all have maps to it, unique maps. Now, one of the things that's really fun about universal constructions is because they're universal, because they are defined by virtue of the network of relationships, we can apply them across categories. It's nothing about the intrinsic nature of the objects in a category, that this is a category of vector spaces, and therefore we have to do this, and this is a category of, involving pre-orders, and we have to do this other thing. No. That's a general rule. And you'll find terminal objects coming up in category after category in ways that are rather pleasing. And again, have this mixture of familiar and sometimes unfamiliar. So the terminal objects in the Boolean pre-order category, where we have two objects, true and false, and where arrows indicate implication. So does whether one thing implies another. We have an arrow from false to true. Given false, true is implied. There's also from true to true and true to false. In any case, the terminal object here, there is a terminal object, and it's true. Because every other object, every object, including itself, has a unique arrow to it. Do you believe that? Are you comfortable with that? It says unique arrow to it. This is a pre-order category. And as such, there's only one or zero arrows between terminal objects. For the divisors of 30 category, 30 is the terminal object. And someone might say, Well, there's no morphism from 3 to 30. What would you say to someone who said there's no morphism from 3 to 30? What would you say? What's that? Yeah, it's a composition, and by composing this or this, there's an arrow. But more than that, I think what Jeff was trying to get at, different word, but at the essential idea, it doesn't matter which way you go, there's only one. But there is one, because by composition you can get here. And we only draw the ones that are direct. We only draw the generators here. We don't draw the things that emerge from them through composition. So there is a link there's a morphism from 3 to 30. Is there one from 2 to 30? Yes. So every object here has a unique morphism here. It's a pre-order category. So if there's a morphism, it has to be unique. Now, if T is a terminal object and T prime is any other object, then the following are equivalent. T prime is a terminal object. If T prime is a terminal object, if and only if T prime is uniquely isomorphic to T, and T prime is isomorphic to T. These all come down to the same things. You can have more than one terminal object, but it has to be uniquely isomorphic they are uniquely isomorphic to each other. And I won't go into that in detail. Now, I want to highlight something here. This is actually really important. I've been talking about terminal objects as having a property. The defining property of them is such that for every object in the category, there's a unique morphism to the terminal object. Keep that in mind. Please keep that in your head, okay? There's unique morphism to the terminal object, okay? Are you comfortable with that? That's why it's terminal, right? Okay, but I'm going to show you another role that they play in categories that's extremely important. Oh, looks like Chris. Okay. So we talked about terminal object being the unique terminus, but terminal objects have another role to play commonly. And I say generalized element, and it's true it's related to that, but it's also even more directly global element, okay? Or more generally, generalized element. Now, this is a concept I'm still fully getting my head entirely around, but it's a familiar one in set, and it'll make sense in many set-like categories and pre-sheaf categories to you intuitively. So the idea here is the terminal object, this one here on the left, serves when it has a source of arrows from it. Remember, what defines it is a unique arrow to it from every other object. But here, if you consider the arrows from the terminal object to a given object, those arrows serve to pick out the points, or I might say elements. So global elements in some general sense of this other object. Let's consider this in set. Can we consider it in set? If you have a set of, if you have the terminal object, that's a set of size 1. I'm telling you, terminal object is a set of size 1. Think about it. I should have shown this, but I should have emphasized this more. This is a set of size 1 that serves as the terminal object. I should have emphasized this earlier, but let's just go through it in our head. Why does every object in a category of set, the category set, where objects are sets, and morphisms are functions. Why does every object have unique morphism, that is function, to this single object? Can you give me an intuition for it?
There's only one way for every element of one
Yeah,
set to map to its element.
That's right.
Emphasize one.
that's right. So it doesn't matter if this other set is it also of size one. There's only one way for it to map here. The everything is fixed, right? Like there's no choice for this for a set of 3 elements. There's no choice either. They all have to map to this single object. There's no choice. Here's an object with 2 elements in it in set. It has no choice. All of these have to map to that. What do you want to order? What's on the menu? Just a single item. Your choice is fixed. How if it were an empty object? How many morphisms are there from that to the terminal object, to the single object? From an empty set. How many? Well, it's one vacuous one. It doesn't have to do any work. It's just, it exists, it's done its job, there's no job to do. It just kind of sits there. There's no elements for it to map from an empty set. So even that has one morphism into the one object set. So one object set in set is terminal. So what I'm showing you here, though, is the terminal object in set as the source of morphisms into another set of size 3. And what I'm claiming is that if it goes into a set with n elements, here n equals 3, how many morphisms are there from this terminal object into this? How many? 3. If this in general has n, there are how many? N. It could go to the first, it could go to the second. Think this isn't set. Are we comfortable with this?
So product of the size of the set, right?
Yes, that's no, it's actually not the product. We'll come to that in just a minute, actually.
Okay.
But here for a terminal object with an object of size 1, you can either go to the first, right? All you have to do is pick which one it goes to, right? Right? Goes to the first, or it goes to the second, or it goes to the third, right? We comfortable with this? And what I'm telling you is that this pattern recurs for categories where you have terminal objects, but it's not necessarily elements it's picking up, but it's kind of picking out some sort of global notion of element or point. And importantly, these morphisms will be different in different categories. What this morphism means. Here it means a function, right? But in a category where this is a causal loop diagram, a pre-sheaf category, a C-set, where this is a causal loop diagram, and this is another causal loop diagram, it's not that this is a function. This is a homomorphism between those diagrams. This is like this diagram being matched in this one, in this one, in this one. And there too, it is picking out elements of sorts. For example, this for causal loop diagrams would consist of a single variable, a single plus loop, and a single minus loop. It has to have each of those, or else not every other diagram could be mapped down into it. And if you try to find that in another causal loop diagram, you will pick out each of the vertices in that other causal loop diagram. But you also pick out different possible matches for the plus arrows and different matches from the minus arrows. So the point is, it's picking out things even for other categories. I won't go into this. I don't fully grok it yet, but the point is, we see this a lot in the use of the terminal object we see a map from the terminal object to another object as kind of picking out something in that other object. Now, here's the terminal object. And here we're going to have an object AB. How many maps are there from AB to the terminal object in set? This is set in set. So this is a singleton set. This is a set of size 2. How many morphisms are there from this to this? Only one. How many morphisms are there from the terminal object to this one? 2. The single element here could go to A, or the single element here could go to B. So all the choices, right? It's only one choice. Are we comfortable with that? Okay. Because Jeff asked about it, I'm going to just build our thinking about it. It's not a bad thing. Okay, here are 2 mystery sets, A and B. Mystery set A on the left has 4 self-arrows, including the identity. Mystery object B on the right, also a set, these are in set, it has 27 self-arrows. There are, furthermore, 8 arrows from B to A and 9 arrows from A to B. Can you figure out what A is? How many elements are in A and how many elements are in B? How many do you think are in A? Okay. So if we think about 2 elements here, how many ways are there to map, let's say, A comma B onto 0 comma 1? In other words, how much, or onto A comma B, yeah, from it to itself. We'll just keep it that way for simplicity. Well, A could go to A, and B could go to B, or, well, maybe I'll make it simpler. A could go to A, B can go to A, or A can go to A and B can go to B, or A can go to B and B can go to A, or A can go to B and B can go to B. There are 4 ways, four possible ways. Are you confident with that? So for each of the 2 elements, there are 2 possible ways to map it to itself. So for A, there's 2 possible ways. It can be mapped to A or it can be mapped to B. So there's 2 there. And then for B, there's 2 ways it can be mapped to A or to B. So we multiplied 2 times 2 is 4. Are we comfortable with this? Okay. Now, there are 9 ways to map from A to B. So what does that imply about what B is? We know there are 2 in A. What does this imply about what B is? 3 elements. Because if we have A, B, and set A, capital A. For A, there could be 3 choices here. And for B, it has 3 choices where to map, independent of that, right? So 3 times 3 would be 9. Are we comfortable? Now let's see, is this consistent with 27 going to itself? Well, for each of those 3, I have 3 possible choices. So I have 3 possible choices for the first, 3 for the second, and 3 for the third, which is 3 times 3 times 3, which is 27. We comfortable with that? Let's do this check. Remember, everything's got to hang together. It's just like a sheet for brief sheet. All the connections, all the mappings have to hold. This has to hold. We have 3 here and 2 here. 2 times 2 times 2. Yeah. For each of these 3, for the first one, there's 2 choices. For the second one, there's 2 choices. For the third one, there's 2 choices. 3. So 2 times 2 times 2, or 2 to the 3rd power, or 8. Are we comfortable with that? So maybe again, this gives some glimpse about this radical notion that like everything we need to know about these sets is given by the morphisms. Like I don't need to know secretly what's inside of A. It's implied by the relationships that it's in. This network of relationships imply all the information we need about A. Are we comfortable with that? That's the notion also of the Oneida limit. Like we can know an object totally through its web of connection. And it's the idea behind these universal constructions in many ways. Okay. Now I'll leave this in the slides, reasons for failing to be an initial object. They're actually worth thinking about, like, okay, there may be, you may be in a category where, imagine the natural numbers arranged by where the objects are natural numbers, the morphisms are, if there's a morphism from A to B, if B is greater than or equal to A. There's an initial object for that. What is that initial object? If we have the natural numbers. What's the initial object here? Zero. Zero. So I'll temporarily stop that. Let's suppose instead we have integers. So we have 0, -1, -2, -3, 1, 2, 3, etc. Right? Does this have an initial? Does this have an initial object?
Under the same rule, no.
No. Yeah, the morphisms. No, it doesn't have an initial object. Does this have a terminal object? No. So you can have cases where these are just a few examples, but where initial objects don't exist, terminal objects don't exist, both might not exist, both can exist. Now, there's an interesting class of categories where they're the same. Initial objects and terminal objects are the same, and those are called zero objects, which is kind of fun. And there's a class of categories called pointed categories, which have these zero objects. Okay. So this is an initial object in Boolean preorder. Are we comfortable with that? This one here. This is initial object in divisors of 30. Okay. So an initial object is in a category is an object I such that for all objects in that category, there exists a unique morphism from the initial object to those other objects. Again, it doesn't have to exist if there are several, they're isomorphic to each other. And it's an example of a colimit. Okay, let me ask, in set, what's the initial object? It'll be very familiar to you. What's the initial object? Empty set. Empty set. Empty set, we have a vacuous map to any other set. It doesn't have to do any work, right? Does it have a vacuous map to the terminal object? The empty object? Yes, it does. It's a terminal object. Yeah. Someone said it earlier. I'll put this as star. Whatever. I mean, just some object with one. Does it have an empty? Does it have a morphism to itself? Yes, it's ID morphism. Yes, it has some morphism and ID function. It's sort of vacuous function. doesn't have to do any work, so there's no problem that it can't like assign elements to its to anywhere because there's no elements to assign. So so it's a bit like saying, I don't know.
0 factorial is 1.
Yeah, like yeah, something like that. That's with monoids. But yeah, it's like I have no money to pay you, that's fine because I have no work for you to do. You know, it's like there's nothing for you to there's no work for you to do here. Okay, so the initial object, the empty set serves as initial. And in the category Hask, where this is going to be a category where we can have sort of analogs for other typed languages. Maybe it's Scala, maybe it's Rust, maybe it's ML or OCaml or what have you. Pure script, what have you, other typed languages. Terminal object is called unit in Hask. It's this one up here. It's just like a type whose only value, it only has one value. That's all it has. It's like a single possible, only one possible value. It's unit. So you can have a function that returns unit. Doesn't return any information. There's also a one called the void, which means nothing. That's quite different from the implication of void in C. But void has no possible values. And it can have maps. It has maps to every other object because these maps are typed functions going from something a type void to the appropriate type. So here's one, for example, from void up to Boolean. So there's no work to do, and it returns a Boolean. By contrast, there's always one unique function from any type, let's say float, to this terminal object. There's a single unique morphism here from the set of floats to this value of unit. All it does is every float is mapped to unit. There's no choice. There's zero choice. Are we okay with this idea? Okay. So I will say, if anyone here has seen functional programming languages, this is quite central to elements of design for some, and I am planning to teach a course on that in another year or so. Okay. So one thing Eugenia Cheng brings out is initial and terminal objects can look rather different. And initial objects can have, even in some that feature a sort of elaborated set, some can have no elements, like initial objects in set, but sometimes they're quite different. And there are these categories where zero objects are both initial and terminal. So sets and functions, we talked, initial is empty set, terminal is singleton set. Posets. How about think about partially ordered sets or pre-orders. So we've seen some of those pre-orders. You can have initial objects. This is actually, we've seen it in a particular poset, in particular pre-order. Here we're talking about the category of posets. So here we'll talk about like category where each object is a pre-order. Each object is one of these pre-order structures, like we were talking about, like division by 30 category or what have you. Morphism here is a map between preorders, which is, we discussed it once, but it's a monotone map, meaning it maps things from this one to here, but in a way that honors the structure. Do you remember that? Like if B is greater than or equal to A here, the map of B is greater than or equal to the map of A here. It honors that because that's honoring the structure in terms of the morphisms, including composition. So these are monotone maps. And what I'm telling you here is that the initial object here is the empty poset. That's kind of familiar from set. The terminal object is the single element poset, where it's greater than or equal to itself. Any poset can be mapped to one, which is, it has a single element that's greater than or equal to itself, because any poset can be mapped onto that and still honor the monotone property that if A is greater than or equal to B in the source, then the map of A will be greater than or equal to the map of B in the target. We comfortable with that? I'm glad to talk about that more in office hours. Monoids. Okay, this is kind of interesting. Category of monoids. Now imagine these are monoids. Individual objects are monoids. And we have monoid homomorphisms between them that sort of collapse some elements down, but in ways that still honor composition. So maybe this is the mod 4 monoid, and this is mod 2 monoid, and this collapses down to the elements. Like this goes in a little circle, A, B, C, D, back to A. Here we have essentially, maybe I'll call it 0, 1, 2, and actually I should have it 3, sorry.
So you know you're still sharing your screen.
Oh, I'm sharing my screen. Thank you. That's super helpful, Jeff. Mess that up diagrammatically. Let me put that in. If these were monoids and this were one with like 0, 1, 2, 3, we might map it down into one with 0, 1. So maybe we map like 0 and 2 to 0, 1 and 3 to 1, and we have this nice homomorphism. We can either map here and then go over, and we'll get the same thing as going over and mapping that. Okay, so here, kind of fun. The initial objects are a one element monoid, not empty, but a one element monoid. That the one element monoid has a unique map to any other monoid. It maps the single possible value to what? What does it map to in the other one? Well, monoids, you remember if we have monoids, we could represent them with we could map here. So in terms of mapping of the elements, I'm struggling about whether to think about monoids as categories with a single element and multiple morphisms, or here monoids as a structure where we have elements and we can add those elements. If we have elements, every mapping, we could map everything onto the identity element, and then identity and identity would just stay to be identity. And so that would be a single element monoid. Terminal is also is also a single, yes, a single element identity monad. Okay, so this is all for the initial and terminal objects. We have just a short time left, but I want to